In part 1 of this video, we discussed the nature of multi-star systems and how they are divided into nested binary stars. We then learned how to define their separation distance, or semi-major axis, as well as their eccentricity, which then allowed us to calculate their periapsis and apoapsis, that is, their closest and farthest distances from one another, respectively. In this video, we'll be adding a third star into the mix and learn how to define its orientation relative to the other stars. Now, in my previous video, I made my stars into a wide binary system so that there is enough room around both stars for the various types of planets that I'm going to build in future episodes. However, such a system is not really conducive to having more stars added to it. So for this video, I've constructed a new system that contains two spectral type F main sequence white stars in a tight binary grouping with a separation of about 0.089 AU with a period of just under 6 days. Their critical parameters are on screen now. To this pair, I will be adding a third star, a spectral type K3 main sequence orange dwarf. Just as when we're adding our second star, the first parameter that we want to define is the new star's average orbital distance, or semi-major axis. When adding additional stars to a binary pair, the new star, or stars, will almost always be in a wide binary configuration with a separation of several hundred to a few thousand astronomical units. However, if you're wanting to have your third star closer than this, which I do advise against, but if you must, you'll need to keep the star's minimum distance, its periapsis, beyond 10 times the maximum separation of the binary pair. Any closer than this and you risk your system being unstable and one of the stars being kicked out of it. So, for example, my AB pair have an apoapsis of a little over 0.1 AU. So my C star should have a periapsis no closer than 1.1 AU. But I want to reiterate that in reality it is very unlikely to have such a compact trinary system. I'm going to give my third star a very realistic and stable semi-major axis value of 2,781 astronomical units. As before, the next parameter that we must define is the new star's eccentricity, which, just as with binary stars, is usually between 0.4 and 0.6. However, unlike with binary stars, which can have low eccentricities when orbiting very close to one another, stars in wide orbits are almost never found with eccentricities below 0.3. I'm going to set my third star's eccentricity to 0.6392 and then use the equations that I covered in the previous video to calculate its periapsis and apoapsis distances. With these parameters, I have defined the shape of the star's orbit, but now I need to define the orbit's orientation relative to the AB pair. To this end, I need to define three more parameters: the star's inclination, longitude of the ascending node, and argument of periapsis. The first of these parameters that I need to set is my C star's inclination. This is the angle between my star's orbital plane and the system's reference plane, which in this case is the orbital plane of the AB pair. Inclinations between 0 and 90 degrees are considered prograde orbits, as the orbiting body revolves in the same direction as the primary object is spinning. Inclinations between 90 and 180 degrees are considered retrograde orbits, as the orbiting body appears to revolve in the opposite direction of the primary's spin when viewing the system from above the primary's north pole. I'm going to set my star's inclination to be a rather steep 62.3 degrees. That takes care of the orbit's vertical component. Next, we need to define its horizontal component. To do that, we use a parameter known as the longitude of the ascending node. This sounds really complicated and confusing, but I promise you it is not. But to understand it, we need to briefly discuss orbital nodes. Orbital nodes are just theoretical points within an orbital path that have some significance. You are already familiar with two nodes, the periapsis and the apoapsis. But for an orbit that has a non-zero inclination, it has two additional nodes, the ascending node and the descending node. As an object orbits on an inclined path, there is a point in its orbit where it passes from below the reference plane to above it. Or, to be more accurate, it moves from south to north of the reference plane. This point is the ascending node, as the object ascends through the reference plane. Consequently, there is a point on the opposite side of its orbit where the orbiting object travels down through the reference plane, passing from north to south. This is, of course, the descending node. While these nodes have some extra significance in astronomy, for our purposes, we will just be using the ascending node as a point of reference for aligning the system. The longitude of the ascending node is therefore just the angle between the origin of longitude and the ascending node. The origin of longitude is just an arbitrary reference direction that acts as a 0-degree mark for these angle measurements. I will likely make a video about the origin of longitude in the future, but for now you don't need to worry about it. Just pick whatever direction you want to represent 0 degrees and then decide the angle at which your star will orbit relative to that, measured in the direction of the orbit. For my C star, I'm going to set its longitude of the ascending node to be 204.26 degrees. If we were dealing with a circular orbit, then this is all we'd need. But because these orbits have eccentricity, we need one final parameter to define how their eccentricity is aligned. This parameter is known as the argument of periapsis and is the angle between the orbit's periapsis and its ascending node, measured in the direction of the orbit. So for instance, here, my C star's periapsis is only about 16 degrees from its ascending node, but it is behind it in its orbit, and I have to measure in the direction of its orbit. So it instead has an angle of approximately 343.65 degrees. Now, you may be looking at these values that I have defined and thinking that they are rather random and arbitrary. And you are absolutely right, they are. But that's okay. In 99% of cases, it's not going to be particularly important to you how your stars are aligned with one another. So you can just choose random values for these parameters and be done with it, because stars can realistically have any combination of these three parameters. In those rare cases where you do care how your stars are aligned, just grab you a protractor and work out the angles that you feel you need. But be aware, just because they are arbitrary doesn't mean you don't need them. Whereas I have classified these as important parameters, that is a bit of an under-evaluation. I feel that they lie somewhere between critical and important, as you can get by without them, but you really shouldn't. They are very important to a multi-star system, particularly those with 3 or more stars. If you ever want to determine which of your stars are visible to which hemisphere of your planet, where in the sky, at what time, and for how long, then you will need these parameters to work that out. Additionally, if you, or any of your fans, ever wish to recreate your system in some kind of simulator, such as Space Engine or Universe Sandbox, then you will need this information. Also note that all of these parameters that we've discussed do not apply only to stars. They apply to all orbits: stars orbiting other stars, planets orbiting stars, moons orbiting planets, and even spacecraft orbiting, well, anything. Speaking of planets, there are 2 types of planetary orbits that can exist in multi-star systems: S-type and P-type. S-type orbits have the planetary body revolving around one of the stars in the system, just as Earth revolves around the Sun. This type of planetary orbit can be found in wide binary systems and some mid-distance binary systems. P-type orbits have the planetary body orbiting 2 stars simultaneously, similar to the way Tatooine from Star Wars revolves around 2 stars. This type of orbit is primarily found in tight binary systems, but it may be possible in some mid-distance binary systems as well. I'm not certain what S and P actually stand for, but the way I remember it is S for single, as in this type the planet orbits a single star, and P for pair, as in this type the planet orbits a pair of stars. With a planet in an S-type orbit around just one of the 2 stars in a binary pair, the main concern is how close the second star comes to that planet's orbit. If the second star's periapsis is too close to the planet's orbit, then that orbit can become unstable. The safe range for planetary orbits is anything less than approximately 20% of the star's periapsis distance. So for example, say we had 2 stars with a periapsis distance of 15 astronomical units. We would multiply that distance by 0.20, the equivalent of 20%, to get the maximum safe distance that a planet could orbit from either of those stars. In this example, that would be a maximum of about 3 astronomical units. For a planet in a p-type orbit around a binary pair, there is an additional inner limit to stability. In such systems, the gravitational pull that an orbiting planet experiences fluctuates as the two stars orbit one another. These fluctuations can disrupt and destabilize a planet's orbit if it is too close. But at distance beyond approximately 3.5 times the maximum separation of the stars, the amplitude of the fluctuations are diminished enough for there to exist stable planetary orbits. So in this case, we would take our star's apoapsis distance and multiply it by 3.5 to get the planet's minimum safe orbital distance. For my stars, their maximum separation, or apoapsis, is just 0.1186 AU. So I would enter that into my calculator and multiply by 3.5 to get the minimum safe distance for a planet. That gives me a value of 0.4151 AU, or about 62 million kilometers. I will need to place my planet at a distance that is beyond this minimum safe distance, but close enough that it receives the right amount of energy from its two stars to be habitable. Now, I have chosen good stars for this as they are very luminous and close together, so my planet could exist very comfortably at an orbital distance of around 2.5 astronomical units. However, this is where you can run into problems if your stars have a low combined luminosity or have too large a separation. In such cases, the distance required to have a habitable temperature may be below the minimum distance needed for stability.